Hello everybody, this is a FET, a simulation showing the photoelectric effect. Essentially here is a metal, in this case it is sodium. We can change it to different metals, but that's sodium metal. And this is light being shined on it. As you can see, I can change the intensity up here to be really intense. Just means more and more photons, or really low intensity, which means not a lot of photons. So let's just keep it kind of in the middle to start with. Notice that shining yellow light on the sodium does nothing, but if we increase the intensity, what about green light? Yep, green light is enough to eject electrons off of the surface of that metal. So the couple questions we have about what would happen with different types of light are two types of questions. At this point, now that there's enough energy to eject it, if we increase the amount of energy in the photons and keep the intensity the same, I would expect them to be ejected at a greater speed because the extra energy is going into those electrons. So let's see what that looks like. So now we have a blue light, which is still removing electrons, but they are at a greater speed, average speed, as far as maybe some of them aren't moving quite as fast. You can see some of these are a little slower still, but overall they're moving faster. And if we put even faster still, you can see that it would cause them to come out even faster with more kinetic energy. Now, I'll just go back to here. Go in the blue range. What would happen if I shine it more intense? Well, more intense just means more photons are being shined on it. So since I'm shining more photons on it, it should remove more electrons, since it's a photon versus electron battle here. So I'm going to increase the intensity, and from that we're seeing more photons overall. Not quite as, oh, there we go, that's a little bit more active. But we see more photons overall. So now let's restart or reset it. I'll put it back to 50. I'll go back to the lowest energy, which is, or I guess IR is the lowest energy, and go to something like zinc. If I go to zinc and I go to red, nothing. Those photons do not have enough energy to kick out electrons. Okay, yellow, nothing. Green, higher energy still, nothing. Blue, nothing. Higher energy blue, nothing. How about purple or violet? Nothing. So for zinc, it looks like we're going to need to get into the UV range. Are we there yet? There'll be a certain wavelength in UV that eventually will be high enough energy to remove those electrons. Don't know for sure what that threshold is. There we are. That's the threshold for zinc. So for sodium, it was way back here somewhere. Didn't need nearly as much energy. But for zinc, it must be holding on to those electrons more tight. So there's a higher, what's called a work function, a higher amount of energy needed to remove them. So let's go back, whoop, and let's try copper. So every element's a little different. There's no way to predict it, but you'd have to do it experimentally. So you can see copper again, nothing with green, nothing with blue, higher level blue, violet, nothing. UV, very similar to zinc in that we need to get somewhere in the UV range. Looks like it's a very similar number to zinc as far as being able to eject it out. And again, just like the the sodium, if I go higher or higher energy, see how they come out way faster. And if I increase the intensity, they should increase the number of electrons that are being removed in that case, just because that means that there's more photons. So when we talk about intensity of light, it's just a brighter light. There's more photons that are being shown on it. So every element's a little bit different. Here we have an unknown element that we could try to figure out. It's definitely not sodium because we're getting nothing in the visible spectrum at all. So not sodium, but we could figure out which one of the ones above it is. If we look at something like calcium, I believe, let's see if we get somewhere in the violet. There we go. There's a little bit of violet light, so the blues didn't do it, but a violet does. So this is called the photoelectric effect. The amount of energy in the photons, if it's high enough, can eject electrons off the surface of the metal. They're actually removed off the surface of metal. Notice how if we get enough of them, we have a current running through a wire. So let's go higher and higher, and notice how the current is starting to give us something. We can charge a battery, we can run a light, lots of different things with those electrons running through a wire. So this is the science behind anything that is solar powered. You are taking electrons that are moving and gather them through a wire and charging a battery in most cases. Sometimes just running it right away, just running through a wire like for a calculator, but like a light in someone's front yard that's solar powered, it actually charges a battery throughout the day, and then once it gets dark at night, then it senses that it's dark, and it with the photoelectric effect also, and the battery then runs and turns the light on. So that is a animation of the photoelectric effect.